Oh, oh. Hey guys, welcome to the video. We're starting the unit about two-dimensional kinematics, in case you're wondering. And so before we actually learn anything about two-dimensional kinematics, we have to actually learn a bit about vectors. But I suppose first I should tell you what two-dimensional kinematics is so you have some kind of a sense of context of where we are going with this. Up to this point, we've only done one-dimensional kinematics, which is that pen fell straight down. All right. Or something rolls down an inclined plane, or maybe up and then down an inclined plane. Right? That's one-dimensional kinematics. Things only move in straight lines. And it's all well and good, but most things don't actually move in straight lines. In fact, there's all kinds of things you may have noticed that you move in some sort of a different motion entirely, such as... Did anybody else see that? It's still bouncing, whatever it is. Well, anyway, that ball went across the screen in sort of a parabola you may have noticed, which is actually how two-dimensional kinematics is going to work in general. I shall reveal my friend the marble launcher. Now, I fired that at, I don't know, something like a 53-degree angle. Had I fired that, of course, at a different angle, its motion would have been different. And the only way that we really have in physics of talking about how this thing fires differently and lands differently than this thing that is fired at maybe the same speed is by breaking up that velocity that it has initially into what are called components. Okay, and then that's going to be crucial in how we do everything with two-dimensional kinematics. There is three-dimensional kinematics, but we're not really going to worry about that. It's the sort of thing that would come up if you were doing really super frickin' long-range artillery, and so you had to worry about this thing called the Coriolis Effect, which is due to the fact that the Earth is rotating while a bullet is in the air. Mostly it doesn't matter. It matters a tiny bit for something like golf, and a lot if you're trying to, I don't know, hit a target on the other side of the world. Fine. But for this class, we're not going to worry about Coriolis effect. We're not going to do three-dimensional kinematics. It's always going to be two-dimensional kinematics, and that's the most complex it will be. Okay, now, we said it was going to all start with vectors. So what are vectors again? Because we did learn about vectors before. All right, now last unit, vectors were just positive, negative. That was it, or maybe positive, negative. The only difference between, like 3 meters per second and 3 meters per second in the other direction was, well, one was left and one was right, or one was up and one was down, and so we just called one positive and one negative. And that was good enough for one-dimensional motion. But when we get into two-dimensional motion, there's a lot more directions that things can go in. And that's what makes a vector, after all, different from any other kind of number, is that it has a direction. Okay, so reminder there then. A vector is something that has a magnitude and a direction, as opposed to a scalar, which just has a magnitude. If you're thinking to yourself, I remember defining that word magnitude. What was that number again? Magnitude is just how big the number is. That's all that term actually means. Okay? So if you see 3 meters per second, the 3 is the magnitude. This is, of course, the unit. And this would be a vector if I did something like put a positive sign in front of it, or say it's at 30 degrees. And now this is the sort of thing that we're going to have to learn how to handle in this unit, is when it's at an angle and not just plus or minus. All right, now, the way that we tackle that is trigonometry. Oh my gosh, triangles again? But I thought it moved in a parabola. Yes, but actually, when we talk about the initial velocity of something that is launched, we're going to have to do this with it. If you launch something like that, it's not just moving sideways. It's not just moving up. It's doing both of those things at the same time. And so when we look at this initial velocity, whatever it is, at whatever this angle is, we will talk about it as though it were, in fact, a triangle. Pretty much all vectors in this unit, and then also the next one, and so on, are going to be treated like triangles, because that's how we talk about their x and y components. So this side would be the x component of this one's velocity. You could imagine that something that is thrown mostly straight up would have a very small x component because it doesn't go this way very quickly. If I throw this marker like that, okay, it had an x component because it went sideways, and also a y component because it went up and then down because of gravity. All right, on the other hand, if I throw it like this, I mean, it still probably has an x and a y component, but they are different in magnitude because the angle at which I threw it was different. Excuse me, I have to find my marker. It's lost forever. Fortunately, I have another one. All right, so this has an x component then, and a y component, because it's moving in two directions at the same time, because that's how most motion actually works, right? As long as you leave the ground. All right, this y component and this x component can be found using trigonometric functions. Okay, so at this point, you should probably be thinking, I should have paid more attention in trigonometry. And if that's the case, then you're going to have a brief review here and some time to figure it out, okay? So let me pause. I'm going to write some trig functions on the board. Trigonometry, sine, cosine, tangent. Whenever we say sine and opposite and hypotenuse, in reference to some sort of a triangle, which side is which is usually at least a little bit relative. So most frequently, in this class anyway, I'm going to give you the angle from the horizontal. So it's almost always going to be that the vertical component is one specific function. The horizontal component is a different trig function, and you'll always be able to use it that way. If for some reason I switch the angle from being from here and it's from this, then the trig functions switch. So you do have to pay a little bit of attention to where the angle is drawn from, but everything is going to be related to these functions here. So let's just take a generic triangle. I know I've already got one here, but take a generic triangle right there. I said I'll always put the angle, pretty much, from the horizontal. So that means it's going to be this angle given to you, not this angle. In your geometry class and trig class and whatever else, they can put the angle anywhere they like pretty much, but it's going to be there. All right, x and y are always going to be perpendicular to each other. So we're always going to have a right triangle. It's never going to be anything else. If this side is the hypotenuse, which it is, if that side's the hypotenuse, and we call it R, then this side, which is the side, stop and think a moment if that's adjacent or opposite, that's the adjacent side. The adjacent side is going to be related to this hypotenuse using the cosine function, because cosine relates adjacent and hypotenuse. Okay, so if I want to know what this side is, which I'll call x, and I want to know what this side is, which we'll call y, in terms of r and theta, then I'm going to use the appropriate trig function. All right, so if I write down cosine theta here, cosine theta is going to be this adjacent side over this hypotenuse, which means that x is r cosine theta. All right, and then a little bit of work later, I can see that sine theta, which is opposite over hypotenuse, sine theta is going to give me that the y component, the side I labeled y, is r times sine theta. That's a y. I promise that's a y. There. That doesn't look much better. All right. Okay. Now, if you're still looking at that and you're like, I don't know what any of that means, well, then you should pay attention to the next video, which I'll also link to. Okay, now, if you're still wondering when are we going to use this, and make sure you say that in a whiny voice, and why would I even care about this? Well, we already said it's going to be related to two-dimensional kinematics, but also to like everything else we're going to do for the rest of the semester. So like when we start doing forces and stuff, unless you only apply forces this way and that way, meaning you never pull or push on at an angle on anything, unless you somehow manage to only have horizontal and vertical forces, you're going to have to worry about components. So it's going to come up all over the place. All right, so make sure you pay close attention in the next video where you find out a little bit more about how to actually break stuff down and then how to take components and put them back together. Oh, that sounds terrible. Okay, just watch the video. You'll be fine. Thanks.